converting chemicals from one form to another. Understanding that requires very high level, very accurate calculations so you can make predictions about how the chemical reactions will work. We see catalysis as one of the killer apps for quantum computing.
Chemistry. It helps make up our world. And yet there are still huge gaps in our understanding of it. Our most powerful classical computers are limited in the chemical modeling they can perform, and in turn, the solutions they can unlock. What solutions could we develop, for example, to address sustainability if we were able to model more complex molecules and reactions efficiently? And what if we are able to do that on a scalable quantum computer? I'm Krista Savori, General Manager of Quantum Systems and Software at Microsoft. Today, I'm traveling to Richland, Washington to meet with Nathan Baker at Pacific Northwest National Laboratory, where we've been partnering to bring the power of quantum to our understanding of chemistry.
Pacific Northwest National Lab, or PNNL as we call it, is a Department of Energy national lab. These laboratories handle large, complex problems of national interest. First and foremost, PNNL is interested in some of the deep problems associated with chemistry. We've been very focused on problems in catalysis. So that is converting chemicals from one form to another. The science of catalysis is trying to understand how that works and use that chemical knowledge to be able to design better ways to carry out that conversion.
So with catalysis, we really want to improve that efficiency and have less dependence on our natural resources.
That's right. Quantum chemistry is the area of computational chemistry that tries to understand how molecules react with one another, what their energies are, and how atoms move around in a chemical reaction. The problem is the level of accuracy we would need to design a new catalyst is something that even the largest computers today are struggling to realize.
Like those behind us.
Like the ones behind us. The excitement around quantum computing is that rather than waiting for a computer that's 1 billion times more powerful than the one behind us, quantum computing could help us get to that accuracy sooner. And with finite resources, working hand in hand with the classical computing techniques that we already have and use every day.
Putting it simply, nature speaks the language of quantum mechanics, and we're now striving to build computers that can do the same. When our technology is built on the same foundational principles as nature, we'll be able to mimic its behavior and harness that power to make an impact on the world around us. Here's an example. Over 100 years ago, the process that allows us to industrially convert nitrogen to ammonia was developed. This process has been critical to artificial fertilizer production, and in turn, has enabled us to produce enough food for a global population of 7 billion. But the process is incredibly resource-intensive, consuming large amounts of our world's precious resources, like natural gas. We want to improve this process for the sake of our environment. To explore this chemical behavior in depth, I'm speaking with Bojana Janowska, a computational chemist here at PNNL, about her work with nitrogenase, an enzyme present in healthy soils.
Well, I have been a computational chemist for quite a few years here at PNNL. My work focuses mostly on studying biological systems, that's enzymes, to study chemical reactions that are relevant to energy applications. One of the enzymes we're studying is nitrogenase. Fertilizers, and specifically ammonia that's used in fertilizers, is a very energy-intensive reaction. It actually uses about 1% of all the energy produced in the world just to convert nitrogen to ammonia. the bacteria that have this enzyme nitrogenase are able to really interconvert this reaction a lot more efficiently under very mild conditions. Nitrogen is very abundant, it's all around us, so we'd love to be able to take that nitrogen, turn it into ammonia, and have our agriculture really feed the world in a way that doesn't really deplete our energy resources. Nature does it best. We've known that for quite some time, and we're trying really hard to understand all the mechanistic details so that we can build whatever it is that we need to put it into a technology.
That's a great phrase to build on, right? With quantum computing, I think we have the opportunity to now compute closer to how nature computes.
Exactly. We have made a lot of progress using classical computers, but we are constantly hitting against the limitations. Having the power of quantum computing would help us move this field very, very far ahead.
We have deep expertise in computational chemistry. What we don't have is the ability to understand how to put that onto a future quantum computing platform. And so it's been a great partnership. We've been able to use the tools, the languages that are coming out of Microsoft to turn these quantum chemistry capabilities into something that we hope will execute on the next generation of computers.
Yeah, it's great to bring together experts from both sides. These quantum algorithms can actually have impact and change solutions. That's
Exactly.
pretty exciting. It's through these cross-industry partnerships that we're truly able to explore the full impact quantum computing can have on our world. Together with PNNL, we're working to develop quantum algorithms to enable better solutions to challenging problems in chemistry. And these quantum algorithms will one day run on a fully scaled quantum computer. When we join together to share knowledge across disciplines, we have an opportunity to revolutionize fields and unlock amazing capabilities to help save our planet.